So we were doing proximal gradient descent. And we proved this for convex functions in the last class. We did theorem 10.3, and that was convergence for convex function. And we try to kind of wrap up two more theorem, which is now there is a corollary 10.4 which says that this algorithm is order of 1 by t complexity. So what this says is that consider the setting of theorem 10.3 that we did in the last class for a given epsilon greater than 0 and step length L. Then we have that t must be greater than or equal to L by epsilon x naught minus x star divided by 2, and if this is the case, then we guarantee that fxt minus fx star is less than or equal to epsilon. Okay, so this is a corollary, so it follows immediately from the theorem. Then we will prove convergence for strongly convex, theorem 10.5, and this is for convergence for strongly convex. So the theorem statement says consider the problem which is again the composite, so which is of the form f plus g, f differentiable and g is non-smooth, and suppose that g is convex, and suppose that g is convex and f is mu strongly convex and L smooth. And we take L greater than or equal to mu greater than 0. These are the constants that we have, Lipschitz constant and the mu for the mu strongly convex. And let us say the algorithm generates xt be the sequence generated by the iterates of generated by PSD algorithm, PGD I mean, proximal gradient descent, and where the step size of this is, we take this to be of this form. Then we have this bound xt plus 1 minus x star is less than or equal to 1 minus gamma mu and xt minus x star. So let us look into this xt plus 1 minus x star. So since this is a proximal gradient descent, these iterates are produced by the proximal operator. Okay, so then xt plus 1 must have been proximal of lambda g of xt minus step length gamma grad of xt. So we use that fact because this is a proximal gradient descent. So xt plus 1 must have been produced by this operator applied on xt minus gamma grad f xt. And for x star also we can write because at x star gradient will be flat and proximal of x star will be the x star itself. So we retrace this back. So we can also write this as lambda g and x star minus lambda grad f x star. Okay, this is valid because grad f star x star being the minima, that term goes away. So then we are left with proximal lambda g of x star, but we know that proximal lambda g of x star will be the x star itself. Okay, so that's valid. And then so proximal is a non-expansive operator, meaning it's one ellipsis. So this means that I can write this as this, and then these arguments subtracted. Okay, so proximal is like a function. So it's like fy minus fx is less than equal to norm y minus x. That's one ellipsis, right? So non-expansive also means one ellipsis. So here we are using this fact that this is xt minus x star I take from that one. So I also do some rearrangements, minus gamma, and then grad f xt minus grad f x star. Okay, so non-expansive operator we use, and one ellipsis, basically that's the same thing, and we bring these terms now. Okay, from here we come here now. Okay, and then we do these expansion now. Okay, a plus b form. So this is our a, this is our b. Okay, so this is equal to norm of xt minus x star whole squared, plus also take the b1 gamma squared grad f xt minus grad f x star squared minus, and then 2ab form. So 2 gamma, let us keep it out, and this is grad f xt minus grad f x star, comma the inner product of this with this xt minus x star. Okay, so then we will use coercivity of f. Basically we will look into these individual terms and see. So our view is this, right? xt plus 1 minus x star is less than equal to some constant times xt minus x star. So this guy is already there. So you can think of 1 times xt minus x star is already there. What we want is that these terms now lead to minus gamma mu, or less than equal to minus gamma mu xt minus x star. Okay, so we will use those conditions on strongly convex and coercivity because of the smoothness. So all this we are supposed to use. So the coercivity of f, which comes from the L smoothness. So this was lemma 2.29. So let us recall. So recall lemma 2.29, and this says that if a function is L smooth, so I will not write the complete thing, so I will say L smooth, then this implies that 1 by 2L grad fy minus grad fx is less than equal to fy minus fx minus grad fx y minus x. Okay, this is what L smooth will implies. So we will use this now, I believe here. This is the one. So our y will be xt and x will become x star. So this will give us a bound for this. Okay, yeah. So then with this we will write gamma square. This implies gamma square norm grad f xt minus grad f x star. Norm is less than equal to 2 gamma square L, and then fxt minus fx star minus grad f star xt minus x star, right? So we have taken y to be xt, x to be x star, and this is the bound we have. So 2L gamma square was already there, so 2L goes there, so hence we have 2L gamma square here. So this is for the second term, and we will do also bound for the last term. So and the strong convexity of f will be used here for the last term. So with strong convexity of f, and this is basically lemma 2.14. So with this we can bound this. So this is minus 2 gamma grad f xt minus grad f x star xt minus x star, and this is equal to 2 gamma grad f xt minus x star minus xt plus 2 gamma grad f x star xt minus x star. I mean, right now I have just done the equality. I have just added and separated. I have not used the strong convexity. So as you can see, I have what I have done is xt minus x star is there. Basically, I just expanded. Okay, I just expanded this term, goes with this. So then I have done some mistake here. It should be a comma here, right? So it's comma. So I split this with this, and then this with this again. It's just a equality now, and we will use strong convexity now, I guess. So this is 2 gamma, and so strong convexity will imply that this will be bounded now. So this is fx star minus fxt minus mu by 2 norm of xt minus x star whole squared, and we leave the second term as it is, grad f star xt minus x star. Okay, we just applied strong convexity on the first term. Okay, and okay, then what do we have? Yeah, so xt minus x star term we can take, because we are on a lookout of for xt minus x star anyway. So we had one of these, and we are looking for minus mu of that as well. Okay, so we got again xt minus x star here. In fact, minus mu gamma we already got. So it seems like other terms I should be able to drop and still keep the upper bound. So it seems like what we were looking for is there. So let's see how others fall out from here, basically. So yeah, exactly. So we had one of these, and then minus mu gamma is exactly there. Remaining term we have to show that it's overall negative, and if I drop, I still keep the upper bound. So with this we will do this simplification, that we take this out. So this is minus gamma mu and norm of xt minus x star, and then remaining terms I keep it as in the form of minus 2 gamma mu minus 2 gamma just gamma I mean fxt minus fx star minus grad f x star, and then xt minus x star. Okay, so we have kept this remaining extra term outside. So now it's a question of are we able, can we kind of drop that, right? So is it overall positive? It is positive because f is convex. Okay, so we will use the fact that f is convex, so this implies that this is positive. So this gamma is positive, so overall this is negative. So dropping this is still makes it less than equal. Okay, so just to combine things, so just to conclude, like we leave it here, we had looked at one term, right? So I think we started from here, right? So we started from here, and then we looked at the second term, grad f xt, and then the third term. So okay, but actually second term is also there, right? So it's not just that. So this is also we have to look at. Well, this is also, well, this is convex again, the same argument, but the problem, the thing is now it is 2 gamma square L minus 2 gamma if I add, or yeah, I add, right? So the gamma square. So these are the terms you are looking at, and we have bounded this separately. So this, let us say our first term. So this is the first term bound we had, and we move this second term here, and we're looking here. Now the idea is that we have to combine these. So this we will keep. This is bounded by this, and this is bounded by that. Now what we wanted we got, right? So what we wanted was this and this. The only thing now is to manage these extra terms and say that these are overall negative. So basically if I add this, which this is common there also, so that, and then so if I take a negative, then this is minus, so then it's 2 gamma minus 2 gamma minus 2 gamma square L. So is this that has to be positive. Okay, 2 gamma minus 2 gamma square L must be positive. Basically, if I get 2 gamma common, then it's 1 minus gamma L. 1 minus gamma L is positive, right? Because gamma is less than 1 over L, so that's positive, and overall it's negative. Okay, that's more or less done. So basically, what we have is we can like we want to conclude this. So what we have is that from here, let us say, okay, I rewrite this again, xt plus 1 minus x star is less than equal to 1 minus gamma mu. So this 1 minus gamma mu xt minus x star, and then plus or let us say minus of 2 gamma minus of 2 gamma, and then 1 minus gamma L, 1 minus gamma L, 1 minus gamma L, and then this term, which is fxt minus fx star minus grad fx star xt minus x star. So this term is positive because f is convex, and this term is positive because gamma is less than 1 by L, and between 0 and 1 by L, so this will be gamma L is less than 1 and greater than 0. So that's overall positive. So overall everything is negative, so we can drop and it still remains upper bound, right? So that's the proof of this. So there is a alternate proof of this. I leave that as an exercise. That's like worked out. So I leave that as an exercise for you to look, because that's the same proof for the same theorem but in an alternative way. So the alternate proof is an exercise, and this is found on page 55. So and then we can move to, I mean what I said, maybe I was mistaken a little bit. What I said in the beginning, so what we have here, right, is a bound on this, right? So so basically if you see this iteratively, right, if you see this iteratively, then let us say you do this iteratively again, so you will have 1 minus gamma mu square, right? So the point is like, how does this help, right? So this is x t plus 1 minus x star, and this is less than equal to, so for t plus 1 I get 1 power, right? So then I will go up to x naught basically. So x naught, and then I will have 1 minus gamma mu t, and then x naught minus x star. Okay, so I can recursively put xt, and then again it will produce 1 minus gamma mu, so that will gamma mu square cube and so on. I keep doing this until I reach x naught. I hope the power is okay. So t, if I keep reducing so t, for t it will be square and so on. Okay, it doesn't matter, okay, 1 or plus 1 or minus 1, but the point here is that as t is growing, this guy is less than 1. Okay, so as t is growing, this guy is going to 0, and this means that the iterate that you have is going towards the optimal. Okay, so this result is directly telling you that your iterates are going towards the optimal. Okay, or sometimes we prove results in other way. Sometimes we say like this: fxt minus fx star is bounded. Okay, and that goes to 0. So in this case, yeah, I mean, if the solution is unique, then it makes sense here. This doesn't necessarily imply that xt is going to x star. Okay, because the function may be non-convex, but we are not into that non-convex case. Okay, that's why we don't worry. Okay, the non-convex functions are like that, right? So what this is saying is that, and these are, let us say, all equal, right? They are all equal to fx star. So so your iterates may be converging to this this f, let us say x1 star. This is f x2 star, f x3 star, but they are all equal. So this x star may be this x star, but what you are converging to is this x star, but what you are comparing is this, and you are happy, right? And that is fine. Okay, but in non-convex case, this kind of situations can come where you are going to there are many minima and you are going to one of them, so that's fine. But here yeah, I have some minima which is apparently unique, and then I exactly go to that. What is the complexity of this? So this is corollary 10.6, and again I leave this corollary proof for you. So in this algorithm, the complexity is 1 by epsilon, log of 1 by epsilon complexity. So this implies that if your iterations are greater than equal to L by mu log 1 by epsilon, then you ensure epsilon accuracy. Xt plus 1 minus x star is less than equal to epsilon x naught minus x star. Okay, so these are the complexity results. When you develop algorithms, then you say that, okay, my algorithm is log 1 by epsilon complexity. Okay, so this is how you compare algorithms. And then I believe the last one that I will do in this notes is this the stochastic variant of this, which is stochastic proximal gradient descent. The proof is long basically. So, and for the strongly convex, I will leave it up to you. So what I will do is that I will attempt a proof of this stochastic proximal, and I don't know if I will finish it today. This what we are doing goes directly into, these are all stochastic optimization methods, and they are used directly into deep learning kind of work. So this is specific to this. We have gone into very much detail, as you have seen more than 10 classes on this. So stochastic proximal gradient descent. So as you can see, it's a proximal gradient descent, but now it's stochastic. So what will change is that in place of grad fx, okay, now we will take it for some sample, right? So f will be now approximated by some fi, because f we know is sum of fi. So we will take this take one of these f out of the many losses computed over the samples, and that's exactly what we do in training of these deep learning ideas. We don't take gradient of the full method, and this is why you are forced to study stochastic methods. Okay, because in the end what you do in practice is you only calculate loss partially, and then the gradient is computed on that loss, and the fact that you pick one of these sample losses, it makes it stochastic. You cannot pick deterministically, okay, because that's also a problem, because then you may be creating some bias by selecting the functions that you want. You want it to be a random, okay. So the samples that I will choose over the losses should be random, and hence this becomes a stochastic gradient, a random variable. So this is the extension that we want to do for the proximal method now. So the setting remains the same. The problem is, again, as I say, these proximal methods are 4 composite functions that we have seen. Okay, these are well suited for that, and many problems have this setting. So this is gx plus fx. Again, I don't have to define. This is the meaning of composite, and where f is a sum of functions here. Okay, 1 by n I equal 1 to n. So this is the setting. This is the function we want to minimize. Fi's are differentiable. So fi differentiable, and g is proper LSC. That's it. Okay, there is no convexity assumed for g. There is no differentiability assumed for g. So any non-smoothness you may have in problem, if you can split it from the smooth part, then proximal is a good method to apply. So we will have some assumptions before we do this proof. So in this proof, we will assume that although g is non-convex in the first variant, in the proof we will assume g is also convex, f is also convex. So convex case, assumption 11.2. So in this we will assume g and fi are both convex, and assumption 11.3, here we assume Fi or L smooth is Li smooth. So if I take a max of this, then all of the F will be L smooth, because each F is bounded by Li. Take a max of that, then each will be bounded by L max also. So we can also say that L max, which is max of Li. Right. So then we can define algorithm which is SPGD, stochastic proximal gradient descent, and this algorithm is IT that comes from 1 to n. N are the number of samples, let's say. Then the update rule is proximal, because we are working with proximal, so this is a proximal method. So xt minus gamma t grad fit xt. So as you can see, the only difference from the proximal gradient descent compared to the stochastic is that the gradients are stochastic now. Okay, and we want to prove a convergence for this type of method. So let us try to prove this. So this is theorem 11.5. So assumptions of both are assumed. So this is like composite sum of L max smooth and composite sum of convex. So FIs are the L, each FIs are eventually a L max smooth, because L max is the max of all, and F and G are both convex. So it's a composite of sum of convex. Then if xt is the sequence generated by proximal stochastic gradient descent, then and with non-increasing step size, non-increasing step sizes between 0 gamma naught less than 1 by 4 L max. So we are saying non-increasing step sizes, let's say those are gamma t, but then the first one we say is the first step size that we took in the first update. We take that to be bounded between 0 and 1 by 4 L max, and we know that the other ones are non-increasing. So this means that they are going to be less than equal to gamma naught. Okay, so in general gamma t will be less than equal to gamma naught. Okay, so then the result says that now we will have to use expectation, because this is stochastic. So f x bar t. So again we are now proving results for the average. Okay, so these are average iterates. Fx bar minus fx star is less than equal to norm of x naught minus x star plus 2 gamma naught fx naught minus fx star, and divided by 2 1 minus 4 gamma naught L max, and then sum of gamma s 0 to t minus 1, and plus 2 sigma star f sum of gamma s squared. So you may have seen this something similar before, 4 gamma naught L max, and then sum of gamma s 0 to t minus 1. In fact, these kind of bounds we have seen, so proofs are also very similar. We are just doing this. So we have seen this before, that there were some of step sizes square on the top and some below, and hence we choose certain choices of the gammas to make it convergent and so on. So the only thing is now we are dealing with proximal gradient descent, but the bound looks a little bit similar. So let us try to do this. What I will do in the proof is that I will not redo things that we have done many times now, like 4 or 5 times we have done those things, like apply convexity. So I don't have to now go through all the details. Okay, so what I will do is that I will leave many of the steps as an exercise so that we can complete this proof. So let us first start by looking at xt plus 1 minus x star. So basically this one 1 by 2 gamma t and minus 1 by 2 gamma t xt minus x star, and if we expand the squares then we get this. So this I will leave this as a homework. Okay, we have done something similar before, so like this I will keep quite a few things like a homework now. So a minus xt and minus xt minus xt plus 1 divided by gamma t and xt plus 1 minus x star. Okay, so why is this equal? You can do that. Okay, there is it's a algebraic manipulation, that's all. Then we look into this guy and see that since xt plus 1 are coming from the proximal, then there was a result that if y is proximal of g x, then p minus x is in the subdifferential of g. Okay, that's the subdifferential result that we are going to invoke here. Xt plus 1 is coming from the proximal of applied to xt, and it's proximal of lambda g, right? So that's something we are going to use here. So since xt plus 1 comes from proximal of gamma t g, and xt minus gamma t grad f j xt. So this is exactly how proximal stochastic gradient descent is. Now by looking at this, we will see, okay, this is equal to this. So then we will claim that xt, not just xt, but like this whole thing, this minus this will be in the subdifferential of gamma, in the subdifferential of gamma g, right? Why did I write t here? So t is for the gamma, right? Yeah. So okay, I have written it below, so this way it should be like this, right? This is gamma t times g. So gamma t is the step length varying from t, and that's exactly the algorithm we have. So there was a result that p is proximal of x, and then x minus p is in the subdifferential of g. So we have done all this. These are properties of the subdifferential. So then we will use that. So then this implies that xt minus xt plus 1 divided by gamma t is in the subdifferential, or in our case, like this whole thing is in the subdifferential. So again, I have done this in the last class. So there is a little bit of simplification, like this minus this is in the subdifferential of this, and then I do the algebraic thing where I keep the grad f on the right, differential on the right, and then say xt plus 1 minus xt plus 1, and divide by the gamma t, and that is in the grad f and plus differential. So this is something I have done. I will not do this again. So this will be in the grad f j xt. This was exactly in the last class. So this subdifferential xt plus 1. Okay, so how we play around with subdifferentials, this is called subdifferential calculus, right? So we have done this in the beginning classes as well. So this guy belongs to here, but this guy is differentiable. So this is something unique, I mean single number, and this is being added to a set, possibly a set, because g may not be differentiable there. So we are looking at possible many derivative subgradients there. So since this is there must exist a eta in the subdifferential for which eta plus this will be equal to this. Okay, so then so there exists eta t plus 1 in the subdifferential of g x t plus 1, such that so then we can write this expression. So from this I can write 1 by 2 gamma t xt plus 1 minus x star minus 1 by 2 gamma t norm of xt minus x star squared, and this we have already written, that was left as a homework, which is equal to xt plus 1 minus xt squared minus grad f j xt, and now I'm writing as grad f x j. This is okay, and then there is eta here, eta t plus 1. So this is eta t plus 1 and xt plus 1 minus x star. So does this simplify? It does not. It may not. So basically we make it more because we will add and subtract. So what are we going to add and subtract? Fxt, basically I believe grad fxt is added and subtracted. So add and subtract grad f xt, and this leads to minus 1 by 2 gamma t xt plus 1 minus xt minus grad f j xt minus grad f xt plus 1 minus x star minus grad f xt plus eta t plus 1 comma, and then xt plus 1 minus x star. Okay, so that's it. Okay, so what we have done is that we have added and subtracted these. Okay, have added and subtracted, so nothing changes. The first one is the positive. Yeah, so first term is negative, and second term, let us say we didn't change anything, so xt minus grad of xt, and the positive was added, and then the negative was outside the next term. Okay, that's fine. So and so they do subtract. Okay, so if I add them, they become the one on the top, because the second argument is common for both. So basically I have to look into this. So their grad of xt gets cancelled, and I get back to the previous. Okay, so we did that, and we will do a decomposition where eta we will keep it with xt plus 1 and minus x star, and then the remaining term we will deal with it separately. Okay, and find a bound for these separately. So what we will do is that eta and xt plus 1 and x star, they will be kept separate. Okay, so so for the last term, so in the last term what we have is minus grad f xt plus eta t plus 1 xt plus 1 minus x star. This is equal to minus eta t plus 1 and xt plus 1 minus x star, and minus grad f xt, right, so minus grad f xt and xt plus 1 minus xt, and plus grad f xt and x star minus xt, right. So what we have done is that we have just taken this eta t plus 1, as I said, and put it separately, and then we will now focus on these two terms. So we have in fact also this one. So 1, let us say this is 2, and let us say this is 3. These are the 3 terms we will try to, and these are all the last terms. Okay, because yeah, so first term we may have to eventually do a recursion, because this is also not really resolved, right? It's on the form of t plus 1 and t, so we may have to come back to that as well. So this is just the last term now. Okay, so there were 3 terms there, and we pick the last term, and last term is now into 3 parts. So individually we will bound this now. So the first term is we use the fact that eta t plus 1 is in the subdifferential of g. So eta t plus 1 is in the subdifferential g at xt plus 1. Then we can write minus eta t plus 1 xt plus 1 minus x star is eta t plus 1 x star minus xt plus 1, and this is less than equal to g x star minus g xt plus 1. Okay, so this is the definition of the eta being a subdifferential. Okay, this is what it means, right? So gy minus gx minus eta y minus x, if this happens, then eta is in the subdifferential of g. Okay, so this is exactly the inequality that it satisfies. Now this is for the first term. For the second term, we use the fact that f is L smooth. So for the L smoothness, basically here this term, I should not look there. So this is the f being L smooth. So we know that in the L smooth definition we have fy minus fx minus grad fx y minus x 1 by L y minus x squared and so on, right? So this is something we are going to use that here. So this means that minus so I should write that this, we are using the fact that this is f is L smooth. So then this implies that minus grad f xt xt plus 1 minus xt is less than equal to L by 2 norm of xt plus 1 minus xt, and then plus fxt, and then minus fxt plus 1. So this is coming from the we are focusing on the second term, and in the second term we have bounded that second term using the L smoothness of f. Now let us look into the third term. So the third term is this guy, and again convexity of F. So I mean here it was L smoothness, and here it was in the negative, but that is in the positive. Then we apply convexity to get the upper bound. Okay, so basically smoothness and convexity give you two ways to have these bounds, right? Usually you encounter this or this. If you encounter this, you are looking for upper bound, and then L smoothness helps. If you are bounding this by upper bound, then convexity is helping you. So that's why in most of the theorems you will have these two, okay, smoothness and convexity. So the third term is bounded by the smoothness. So F is so I mean convexity of F. So then this gives me grad F xt, x star minus xt is less than equal to fx star minus fxt. Okay, so with this we have bound for the last term of the previous term. Okay, so so let's see where we are now, and so then we will go back to the first expression that we wrote. So we can write hence 1 by 2 gamma t. So we started with this 1 by 2 gamma t xt plus 1 minus x star squared minus 1 by 2 gamma t xt minus x star whole squared. And in this we had the first term, if you recall, we had minus 1 by gamma t, 1 by 2 gamma t, and this was with this xt plus 1 minus xt, and this we didn't touch at that time. But then we found that we had this additional term xt plus 1 minus xt, so we club it there as well. So this is plus L by 2 xt plus 1 minus xt squared minus, and then we have fxt plus 1 minus fx star. So why did so now fxt came, the capital F. Capital F is when f and g combine. So so when we are looking into this first term and second term, then what we see is that f and g will combine, the negative of that, so that will be minus capital F fxt plus 1. So that we got, and the other term, first term, second term, and third term have fx star, right? And there is a gx star here. So those will get added to give you capital F x star. Okay, so these two are valid. Okay, so this is like minus f xt plus 1 minus fx star. Yeah. So this is in the parenthesis, and then the remaining term is with the fxj, right? Grad f, that was the second term that we wrote. Okay, when we rubbed that, so there was that term with the grad f j xt. So I will just write that. Okay, so you can check all these things later also in the notes. So this becomes minus grad f, what was that, j xt, and then minus grad f xt and xt plus 1 minus x star, and this, okay, so this was the term. So are this all right? That this what we are trying to verify, that look, let us take things that we have done, right? So this was taken care of. This was, we remember, it was on the was the first term. Then small fxt, okay, that got cancelled eventually, right? So I can write this as dotted cancel when I added. Then that's why you don't see this fxt term anymore. And then minus fxt plus 1 gxt plus 1 became capital fxt plus 1 gx star plus fx star became capital fx star, and then that was the term that was there. Okay, you have to trust me. So then we have, and then we will I believe we will drop the term with the L. It seems like overall this guy is negative. So if I drop it, I still remain an upper bound. So why it should be negative? It's like take the common. So it's half of L minus 1 by L minus 1 by gamma t, and gamma t is less than 1 by L. So overall it's, I believe, greater than 1. Okay, so here we can do this very quickly, right? So this is half. Just look into this constants, right? So they should be overall negative, because norm, there is no chance here norm because it's positive. So the only way overall it will be negative is when the constants are negative. So this is oh, this was positive. Okay, it perfectly matched. So I was thinking this was also negative, but that was actually positive. So this is half of L minus 1 by gamma t. Now the question is this overall negative, right? And gamma t was in 0 1 by L, right? So L gamma t and gamma, actually gamma 0 was in there. So basically gamma 0, let me check again for sure. Okay, gamma 0, yeah, actually gamma 0 was less than 1 by 4 L max, right? So there is a different condition here. Then gamma 0 was less than 1 by 4 L max, so we have to work out a little bit. I think this thing is clear, so let us rub this out to have a workspace. So all this is verified. So half L minus gamma half L minus 1 by gamma t. I hope I'm not missing anything. Half of L minus 1 by gamma t. And we want to drop this, and we can drop this if it's negative. And what we know is, what we are given is gamma 0 greater than 0 less than 1 by 4 L max. I mean, what it implies is I can multiply by the L max on the both sides. So 0 less than 4 L max gamma naught is less than 1. So from there we have L gamma t, but each of the L are eventually less than L max. So this is 1 by 2 gamma t. Gamma t is positive, so we don't care. So here what we are left with is L gamma t minus 1. Now L is less than L max. So L max gamma t. So L gamma t is less than L max, because L max was the max and gamma t. So this is still less than 4 L max gamma t, and this is less than 1. So eventually this is less than 1, and hence it's negative. I hope I have not made a mistake. You can verify this again as an exercise. So this seems that this is again negative, and if this is negative, then we can drop it and still remain. So this guy is overall less than or equal to 0, and then it allows us to keep an upper bound with the last two terms there. So this is less than equal to, eventually this is less than equal to minus f x t plus 1 minus fx star and minus grad f j xt. Here the j that you are seeing is stands for it. Okay, I have not, maybe this is a shorthand for it. So basically the sample that you are picking randomly. Okay, so we are just using that. So we are left with grad f j xt and then minus of grad f xt, and let us remove this. So this is minus grad f xt and xt plus 1 minus x star. So we still have 1.5 page. Let's see how much we can complete. So so we have, if you look into the theorem, then we have something like this. Although here we have x naught and so on, that may be retrieved from recursion, I believe, but this inner product is certainly not there in the bound. So it seems like we have to work further on this inner product. So we have to control this. Okay, so the note says that we have to control the last term, and so to shorten the computation, we can introduce some operators. Okay, so let us introduce these operator. So let us define these operator, which is identity minus gamma t grad f, and there is another operator t hat defined as identity minus gamma t grad f j. So note in particular that xt plus 1 is proximal. So we use this, we write this in this new notation here, gamma t g, and this could be written as t hat of xt, which we agree proximal is indeed xt plus 1 prox, and in place of this, if I apply to the operator t hat, if I apply xt, then it will be indeed xt minus gamma t grad f j xt. So in this notation it's okay. And So then we look into this. Okay, this is our focus right now. So let us see what this becomes. So this is minus grad f j xt minus grad f xt, and then xt plus 1 minus x star, right? And then this is equal to, so what I will do here is we will add and subtract proximal txt, and this I mean xt plus 1 that can be replaced, I mean this xt plus 1 this can be replaced by this proximal. That's fine. And basically we do that as one step, and we also add and subtract proximal of txt as an additional. Okay, that will later help us in the fact that this is non-expensive and so on. So we do this as a as these two things now. So minus grad f j xt minus grad f xt, and then proximal of gamma tg t hat xt, and then minus of proximal of gamma tg t xt, and then we have another one grad f j xt minus grad f xt, and then we have this the first one we subtracted, we are like adding that. So proximal of gamma tg t xt, and then minus x star. Okay, so we fed this in one board, but I hope it's not very confused, because that continues here. This is grad f j xt minus grad f xt proximal t hat xt, and this is nothing here. Okay, so this is minus of proximal gamma t txt. So this is what we subtracted and we added. Subtracted and added because there is a negative, so negative makes it positive, but for this guy it's negative. Okay, so we added and subtracted. Now let us see what would be the consequence of this. So observe that the last term in expectation is equal to 0. So the last term is this term. It starts from here and it ends here. So this in expectation is 0. Why is that? That's the first argument. First argument of the inner product is 0, because we know that in expectation fj is equal to grad f xt. So in expectation that term will go away. So that's the argument, and so we can drop that second term basically, because eventually we are planning to take expectation later on. So the idea is that the notes takes that why keep it around, just drop this. In expectation it will go away in future, so just keep the first term. Now if you keep the first term, so in the notes, like I will just write down here, taking expectation with xt, last term becomes 0. Okay, so then we only look into the first term here and apply the non-expansiveness property and so on, right? So let us see what it leads to. So this is our first term, grad f j xt minus grad f xt proximal of lambda, I mean not lambda, gamma t and g, and t hat xt minus proximal of gamma t g of t xt. Okay, this is the first term, right? And the proximal bracket will close here. So this is our first term, and I believe Cauchy-Schwarz is applied, it seems. Okay, it doesn't matter, we can absorb the negative inside and take the Cauchy-Schwarz, and then we have the norm of this. So less than equal to norm of norm of this, anyway it's like less than equal to norm anyway. So this is less than equal to norm of grad f j xt minus grad f xt, and then norm of t hat xt minus t xt. So we have done here two things. We have taken Cauchy-Schwarz And we have also taken the fact that non-expansiveness of proximal. Okay, these are the two things we have used here. Proximals are basically one ellipsis. So it was originally norm of prox t hat minus prox t, but then that itself was less than equal to t hat, norm of t hat minus t. So now if we look into t hat and t, right? So is this remain bounded with yeah, because they get cancelled as well, because both are applied to xt, so identity gets cancelled. So what you're left with is gamma t, and let us say t hat is first. So gamma grad fj xt minus grad f xt, which is also the first term. So overall it becomes a square with the gamma t. So this is less than equal to gamma t norm of grad f j xt minus grad f xt norm squared. If you recall, we dropped this guy with a view in the future that we are going to take expectation. So now we are going to do that. So if we do the expectation now, then this was the term we had basically. Yeah, so we were working with this. Is this already written? That's what I'm thinking. We were, yeah, basically this term. Okay, so we will apply expectation here. So we are still with this term, right? So this term we are tracing it here, and now we are saying let us take expectation of this. So this term goes away. So basically we will apply expectation only on this. So taking expectations, so if we take an expectation, then we can use that. So if we take expectation of this guy, then we have expectation of minus grad f j xt minus grad f xt xt plus 1 minus x star, and this is less than equal to gamma t expectation of norm of grad f j xt minus grad f xt norm squared. And this is the variance, because this guy is the expectation of this, right? So this is x minus mu whole square form. So this is the variance of this is the variance of grad f j xt. So this is equal to gamma t variance of grad f j xt. Now we move to we go back to that f capital Fx minus term that I just removed here, right? So now we will trace that bound, which was our basically the original bound. So inserting this in our inequality, so using this above, because we don't have the knowledge of that equation, so we just say using above, and then we write it as using the above. Then we have that expectation of yeah, so expectation of norm of xt plus 1 minus x star minus half of expectation of xt minus x star whole squared is less than equal to minus gamma t expectation of f of xt plus 1 minus fx star, and plus gamma, this last term that we have, gamma t variance of grad f j xt, right? So this is the current complete bound we have in hand, and still there is one more page on this, right? So this is the longest theorem that we have done so far, and we may not be able to complete it today, but let's see. So like where I will get stuck, I will stop. That's the point. So this is the variance. So to control the variance term, we use the variance transfer lemma. Okay, so this is something we recall from the previous thing. This was chapter 8 that we used. So we'll use the variance transfer lemma. So that we have to kind of recall. To control the variance, we basically here variance of grad f. Yeah, I mean it's written in I, but what we know is that one. So it's like generic sum grad fi type gradients, if I have to control the variance, then we usually use a variance transfer lemma, and which so use variance transfer lemma. And this was 8.20, okay, and with x equals xt and y equals x star. So once again, these verifications of checking this lemma and so on, I leave this up to you because we have used this many times. So we'll just assume that this lemma is used correctly, okay, and then proceed. Okay, so if we do that, then we can bound this variance grad fi xt given. So we have this conditioned expectations that we have taken. So I mean, given xt, this is bounded like this. So it's 4 L max df of xt x star plus 2 sigma f star. Okay, so these are from the variance transfer lemma. We just take it as a truth, and then so this is further less than equal to 4 L max fx t minus fx star plus 2 sigma star f. So all this is from the variance transfer lemma. We may check that separately. So let us assume that all this is true, taking expectations above and inserting this inequality for the variance transfer. So basically we are focusing here. So we have these expectations, and then we will substitute this as an upper bound. So taking expectation, then what we have, basically we will just replace this guy. Okay, our focus is just this guy, and we keep this as it is. So then we have half of expectation of xt plus 1 minus x star squared minus half of expectation of norm of xt minus x star whole squared is less than equal to, so we have this guy minus gamma t expectation, so minus fx t plus 1 minus fx star and plus 4 gamma t squared L max and expectation of fxt minus fx star plus 2 gamma t square sigma star f. So it will be okay if I do it in the next class.